Imagine a battlefield in the future. A 1 megawatt laser turret, mounted on a heavy truck, fires brilliant green beams of light, powered by a compact 100 kilowatt-hour battery. It can sustain continuous firing for about 6 minutes. The entire system fits inside a standard shipping container and travels with most heavy trucks. Hook it up to the truck's 500 horsepower engine via a generator, and the battery recharges in roughly 16 minutes. This laser focuses the beam to a tight 5-centimeter spot at 50 kilometers. At that range, the intensity reaches an astonishing 50 kilowatts per square centimeter, enough to melt through metal almost instantly. Now, picture the targets. A radar detects 4 low-flying jet aircraft racing in. Normally, pilots get 40 to 60 seconds after their warning receiver lights up to release ordnance and dive behind the horizon. But lasers move at the speed of light. Within 200 milliseconds of firing, the first aircraft erupts into a fireball. The entire engagement ends in under 4 seconds. This isn't science fiction. High-energy laser weapons are already being deployed in live conflict zones today. They're transforming how wars are fought. Let's explore how they work and what the impending era of laser weapons means for future warfare. Militaries worldwide are investing hundreds of millions annually in direct energy systems.
A diode laser
They're
is like
mounting
a
them
solar
on
cell in
trucks,
reverse.
ships, and aircraft,
Electricity excites
and
electrons,
integrating
emitting
them into
photons that
air
form a coherent
defenses.
beam between mirrors.
Why the rush? Everyday lasers you know are weak. Laser pointers output mere milliwatts. A laser light shows reach a few tens of watts. As light, they can dazzle sensors and damage eyes because the
Target
energy
acquired.
is tightly
Range 1250
concentrated.
meters.
Military
Confirmed.
rangefinders and
1248
designators
meters.
are only slightly more powerful. They just need to bounce light off a target. A true laser weapon does something far more destructive. It delivers tens of thousands of watts onto a pinpoint spot, heating the target like dozens of blowtorches focused on one area. Today's most advanced systems reach 100 to 300 kilowatts, equivalent to detonating a stick of TNT on the target every few seconds. But militaries dream
Initiating
of
flash
megawatt-class
sequence
weapons.
now.
Green wavelength beams
Stimulation
focused
chief,
by
we
a
have
1
code
meter
ring it.
mirror for maximum range and intensity. Here's what they could do. Swarms of drones would vanish in the blink of an eye, as fast as the turret can slew between targets. Waves of over 100 incoming missiles could be neutralized before reaching their goal, all without reloading. Low-orbit satellites could have solar panels hold or cameras fried. Yet lasers aren't invincible. They need radar or other sensors for targeting, work only in line of sight, struggle with heavy armor or targets behind terrain, and demand massive electrical power. So, why haven't they taken over already? Lasers have existed for over 60 years. In 1960, Theodore Maiman, building on ideas from Gordon Gould,
Toxic
fired
leaks,
the first
corrosive
laser.
damage, and
A
limited
ruby
fuel
crystal
doomed
pumped
the
by
Wild
flash
One.
lamps produced a
Billions
brief pulse
spent,
of coherent
programmed.
red light. Excited chromium atoms release photons that bounce between mirrors, amplifying into a synchronized beam. Early lasers were inefficient pulses. Engineers experimented with dyes, explosives, even nuclear pumps. Most proved impractical. Success came with fiber lasers and semiconductor diode lasers. Fiber lasers pump light through a long optical fiber doped with rare earth elements like terbium or neodymium. The length allows repeated energy absorption and emission, producing a high-quality beam. Semiconductor lasers work like solar cells in reverse. Electricity excites electrons in materials like gallium arsenide, releasing photons that form a beam between microscopic mirrors. Both run on electricity, operate at manageable temperatures, scale easily, and pair well with frequency-doubling crystals that convert infrared to visible green light. That's why lasers now cut steel, scan barcodes, power fiber optic internet, and why militaries use them for gyroscopes, secure comms bomb guidance, and dazzling enemy sensors. The leap to weapons required solving two big problems: generating enough power at range and delivering it through the atmosphere. Spot size at distance depends on wavelength, beam quality, and focusing mirror diameter. A 1-meter mirror dramatically tightens the beam compared to smaller optics. Intensity, power divided by spot area, must overcome the target's hardness, the energy needed to damage it per square centimeter. Drones might need 1 kJ/cm superscript 2 to destroy. Missiles or aircraft require tens of kJ/cm superscript 2. Re-entry vehicles are far tougher. A 10 kilowatts laser might take seconds to minutes to defeat simple targets. That's why thresholds are roughly 10 kilowatts for drones, 100 kilowatts for short-range missiles, and megawatts for jets or hardened threats. Doubling mirror diameter quadruples intensity, but size limits practicality. Higher power is the main path forward. Early attempts at megawatt lasers had major flaws. The USYL-1 airborne laser, a megawatt chemical oxygen iodine laser coil on a Boeing 747, could theoretically destroy missiles in boost phase. But toxic fuels, corrosive exhaust, and limited shots, about 20 per flight, made it a dead end. The program was canceled in 2011 after billions spent. CO2 gas lasers offered simpler chemistry, but poorer focusing due to longer wavelengths, limiting range. Modern solid-state systems changed everything. Today's weapons combine dozens or hundreds of lower power fiber or semiconductor lasers into one high-quality beam. Israel's Iron Beam 100 kilowatts class is now operationally deployed for countering rockets, mortars, and drones at low cost. The U.S. Navy's Helios 60 kilowatts class, with growth potential, is installed on destroyers like USS Preble and has successfully engaged drones. Lockheed Martin and others are scaling toward 300 to 500 kilowatt systems, with Army prototypes testing 50 kilowatts on Strykers and pushing higher. Efficiencies have reached 30 to 50%, making them compact enough for trucks, ships, or even fighter pods. But power means nothing if the beam can't reach the target. Atmosphere scatters light with dust, clouds, and water vapor. Gases absorb certain wavelengths. Turbulence bends a beam like a funhouse mirror, causing twinkling stars or mirages. Solutions include choosing optimal wavelengths, visible green or select infrared, adaptive optics that measure distortions in real time and correct them with deformable mirrors, and techniques to clear paths through fog or dust, short pulses to shatter droplets or shock waves. Heavy weather remains challenging, but progress continues. Cost is plummeting. Cold War programs cost billions. A modern 60 to 250 kilowatt system is already competitive with missiles or guns, with ammunition costing pennies per shot. Commercial laser tech doubles in power, while dropping in price roughly every 5 years. Trends carrying over to military versions. By decade's end, megawatt-class systems could cost only a few $1 million, comparable to a tank. What does widespread deployment mean for warfare? Mobile 1 megawatt lasers would dominate short to medium range air defense, vaporizing drone swarms or missile barges indefinitely. Attackers would hug the ground, limiting range and forcing infrequent mass strikes, reducing overall effectiveness. Aircraft would need advanced stealth, standoff weapons, or a higher cost to survive. Large laser-armed gunships could create massive exclusion zones, turning bombers into offensive powerhouses. Satellites in low orbit become vulnerable. A single ground-based megawatt laser could degrade or destroy constellations over time for pennies. This restricts battlefield awareness, compounding advantages for ground forces. Tanks and artillery regain freedom of maneuver as aerial threats diminish. Naval fleets gain near impenetrable point defense, favoring concentrated task forces over dispersed operations, a potential edge for powers operating in confined waters. Ballistic missiles and hypersonics aren't obsolete, but defending against them gets cheaper for some nations. Nuclear deterrence shifts subtly. Smaller arsenals face higher risk of partial interception. Overall, lasers favor defenders and nations with strong ground/naval forces. Western air-centric doctrines face the biggest disruption, while mass conventional armies gain relative strength. Drones, missiles, and aircraft evolve, becoming stealthier, lower flying, or more numerous, but none disappear. We can't predict every battlefield surprise, but the barriers to practical laser weapons are falling fast. When megawatt systems proliferate, warfare will change profoundly, favoring speed-of-light precision over brute kinetic force. Progress always depends on the right tools. Onshape is one I rely on, a full professional CAD and PDM platform that runs entirely in your browser. No installs, no hardware limits. Just design from any device, anywhere. Real-time collaboration like Google Docs, automatic version history. Branching and merging like GitHub. It's perfect for engineers, teams, or even quick personal projects. Engineers and companies can try the professional version free for up to 6 months. Check it out at onshape.pro/realengineering. This version is tighter, reduced repetition, more accurate, e.g., iron beam is 100 kilowatts and deployed, Helios 60 kW, YL 1 cancellation details, and maintains strong narrative drive